This tutorial is about normal distribution. The normal distribution is one of the most important distributions in statistics and probability because it is the foundation for many inferential statistics such as student t-test, ANOVA analysis, and regression analysis. In this lecture, we'll focus on what the normal distribution is and its properties. We also look into why the normal distribution is important in statistics and probability. Before we answer what the normal distribution is, we analyze how human height is distributed. This is the histogram that shows the frequency distribution of the human height. As you can see, the height of most of us centers at the middle of the graph around the population mean. The number of people who are extremely short and tall are very small and are distributed in the tails of the histogram. You can see the frequency distribution of human height has a bell shape and is symmetrical. The normal distribution occurs for many variables in nature, such as weight, height, volume, blood pressure, and many more. This distribution is called normal distribution, and the density equation of this distribution was established by Carl Friedrich Gauss. So, up to now, we can briefly say a normal distribution describes the frequency distribution of many variables in nature. The curve is bell-shaped, symmetrical, and asymptotic to the x-axis. These are the common features of the normal distribution. However, the height and the width of the distribution varies depending on the properties of populations. For example, the normal distribution of male babies' height at birth is narrower but higher compared to the normal distribution of male adults' height. That means the range of babies' height is smaller than the range of adults' height, or we can say the dispersion in the adult's height is larger than in the baby's height. Why does this happen? Because the deviation of baby's height from the mean is much smaller than the deviations in the adult's height. So, clearly, the height and the width of the normal distribution are defined by the deviations of observations from the mean. That is called standard deviation. And the standard deviation of the height in adults is greater than in the babies. Another thing you may consider is the position of the distribution. Clearly, the distribution of baby's height locates far in the left when compared with the distribution of adults' height. Another example is the distribution of the European's weight is located far on the right compared with the distribution of the Asian's weight. In these cases, the mean of the distributions defines their positions on the x-axis. Therefore, the normal distribution is defined by mean and standard deviation and is normally written as x tilde n mu sigma, in which x is the variable of interest, n stands for normal distribution, mu is the mean of the population, and sigma is the standard deviation of the population. The mean defines the position of the distribution on the x-axis, while the standard deviation defines the shape of the distribution. For example, when the population mean increases, the distribution moves to the right and vice versa. When the standard deviation reduces, the height of the distribution increases, but the width decreases. In contrast, when the standard deviation increases, the height of the distribution decreases, but the width increases. The distribution of a population can be standardized by converting the values of observations into the Z-score. This is the equation for the conversion or standardization. X is the observation's value, mu is the mean of the population, and sigma is the standard deviation of the population. The normal distribution of the Z-score is called standard normal distribution. The standard normal distribution and the original distribution are different in values in the x-axis, but mathematically they are similar. In the original distribution, the mean is the mean of the population, but this mean is 0 in the standardized normal distribution. In the standard normal distribution, we can divide the distribution into sections based on the Z-score. Z-score from minus 1.96 to 1.96 accounts for more than 95% of the population. Z-scores determining 95, 99, and 99.9% of the population in the middle area of the distribution are critical values for hypothetical tests and population estimation. So, we can say the normal distribution is important for inferential statistics. The question is, why it is the foundation for inferential statistics? Let's consider these questions. The first question is how we can identify the height of a type of tree in a forest, such as the Amazon rainforest. Another question is how we can measure the weight of a type of fish in the ocean. Are we going to get the height of all the trees and the weight of all the fish? It's impossible. In practice, we collect the heights of a group of the trees and the weights of a number of the fish, and then we estimate the mean of the height of the trees and the weight of the fish. How can we estimate the fish weight from a sample? It is based on the central limit theorem, and this is based on the normal distribution. The central limit theorem says that, regardless of whether the population has a normal, skewed, uniform, or any other distributions, the sampling distribution of the mean will always be normally distributed, as long as the sample size is large enough. The central limit theorem also says that the mean of the sampling distribution is the mean of the population, and the standard deviation of the sampling distribution equals the standard deviation of the population divided by the sample size. So, if we collect many fish samples with a suitable sample size, we'll have a sampling distribution of the mean, and this distribution is normal. And the mean of this distribution is the mean of the population. However, in real life, we do not collect many samples to estimate the fish weight, but we often collect only one sample. Then we use this sample to estimate the mean of the population. In this case, we use the mean of the sample as the point for estimation. We use the standard deviation or standard error of the sampling distribution to estimate the confidence interval for the estimation. If we do not know the standard deviation of the population, we can use the standard deviation of the sample to estimate the standard deviation of the sampling distribution. Based on the standard normal distribution, we can estimate the lower and upper limit of the mean for confidence interval, such as 95%, from the mean and the estimated standard deviation of sampling distribution. For example, from a sample of 30 fish, which has the average weight of 4.5 kilograms, and the population standard deviation is 0.4, we can calculate the standard deviation of the sampling distribution. We then can calculate the lower and upper limit of the estimation for the mean of the population. The central limit theorem is also true for the sampling distribution of the difference between means. It means that the sampling distribution of the difference between means is normally distributed, and its mean equals the difference between the means of two populations. The standard deviation of the distribution can also be calculated based on the standard deviation of the populations and the sample sizes. Therefore, the sampling distribution of the difference is the foundation to estimate the difference between population means, or to test if two population means are different. This is for today. I hope you enjoy my lecture. See you next time. Thank you.